In Interstellar, Dr. Cooper leaves Earth behind to save humanity, but space isn't gentle with the human body. While Cooper navigates wormholes, black holes, and time bending around Gargantua, his body is also facing something more personal. Without the constant pull of gravity, his skeletal system begins to weaken, silently, invisibly.
It's not just science fiction. In real life, astronauts lose up to 1 to 2% of their bone mass every month in space. That's like aging decades in just a few months. Astronauts' loss of bone mass in space is explained by the Wolff's law. Bone adapts to the forces placed on it, hence no mechanical stress, no growth of bone.
But here's the catch. You don't need to cross a black hole to suffer the same fate. Here on Earth, your bones can weaken for the exact same reason, especially when we use medical implants that are too stiff. They absorb the load, leaving the bone with nothing to do. It's called stress shielding, and just like in space, the bone starts to disappear.
To understand why stress shielding happens, we need to talk about stiffness, and that's where Young's modulus comes in. Young's modulus, also called the elastic modulus, it's defined as the ratio of stress to strain, or in other words, how much force is needed to elastically stretch or compress a material. Hence, it measures how much a material resists elastic deformation under load. The higher the value, the stiffer the material.
Cortical bone has a modulus of about 20 gigapascals, depending on the type. Titanium, around 110 gigapascals. In stainless steel and cobalt chromium alloys, even higher, up to 220 gigapascals. That means these metals are much stiffer than bone. So, when they're used in implants, they carry most of the load, not the bone. The result? According to Wolff's law, no load, no bone growth. Over time, the surrounding bone can thin out, resorb, and even fail, leading to implant loosening, pain, and revision surgeries.
That's why material scientists and biomedical engineers are looking for ways to design implants that mimic bone properties, not just in shape, but in mechanical behavior. One solution? Using porous metals or 3D printed structures that reduce stiffness and allow stress to transfer more evenly to the bone. Materials like titanium foams or shape memory alloys are changing the way we think about implants. It's not just about being strong, it's about being smart.
From astronauts in orbit to patients here on Earth, the stress your bones feel is essential to keeping them healthy. Whether it's outer space or inner space, the lesson is the same: no stress, no strength.